So I'd like to welcome everyone. So good morning, Professor Rao, and good afternoon, everyone. I'm Giulia. I'm a member of the board of PIaneta, and I will introduce you briefly to our association before leaving the floor to the conference. PIaneta is a network born in January 2020 around the University of Pisa, and today it counts more than 20 active members. We are part of the national network ELIES, which unites the different local associations in Italy. Our goal is to disseminate and raise people's awareness about energy and environmental issues, which is why we organize conferences such as the one held today. If you are interested, you can follow us on our social media and you can become a member whenever you want. Today, it is our greatest pleasure to organize this event because it allows us to bring the academic world closer to students with a different purpose than the usual ones. We kindly ask you to mute yourself and switch off the camera during the conference in order to have a stable connection. At the end, there will be time for questions that you can ask by turning on the microphone or by writing them in the chat, preferably in English. Now I leave the floor to Professor Desideri, who will introduce you to the topic of the conference. Thank you from the World PIaneta Association for being here, eager to discover more about energy. Enjoy.
Thank you for the introduction. I thank you for asking me to organize this event, and it's been a pleasure to do it because I'm always very happy when we have people talking with the students and sharing experience and sharing their life and professional developments during their lives in the field of interest, of common interest, which is energy. I'm also very thankful to Dr. Ashok Rao for accepting in a very short time to hold this seminar, because this has made that this is easier now with these tools, because you don't have to move from home and we don't have to organize travel and accommodation. But unfortunately, I must say, this is not the best solution. I really hope that in the future we can continue again having in person and having people coming, inviting people to come. But in this occasion, I must say, I'm very happy because in less than 3 weeks we could organize these, and this would have been impossible in other ways. Well, the topic has been selected mostly because the career of Dr. Rao, you will learn from his talk, has been devoted mainly to gas turbine technology, both in industry for a long time and in academia later, in the latest years. I'm very happy that he accepted, because when I was a PhD student many years ago now, in 1992, I started studying one of his patents, and then after publishing the first papers about those studies, he wrote to the professor I was working with, and he said he did some compliments, and he did some comments about what we had written, and then after that we actually had some more contacts, and in the end we knew each other in person at a conference in Germany in the year 2000. I must say that I'm very happy to have known Dr. Rao, because in addition of being a very good and reputed scientist, he's also been an innovator in our field, because he has been patenting a lot of different ideas. And I think that is also something I asked him to share with you, because patenting is a very tough subject, and holding so many patents is not common in our field. The topic is innovation in gas turbine technology. Turbines have had some, let's say, in the last years we have been talking much less about gas turbines, but now that we need a lot of flexibility in our power grids, we are and due also to the great developments in gas turbine technology and in efficiency and in the ease of controlling and switching them on and off much more easily than other power plants. Gas turbines are returning also in simple cycle configuration as a way to keep our power grid stable, and probably they will have let's say, a second wave also for their technologies applied to power generation. So as you can see, there is no. I always say to the students, there is not now just one optimal solution, but there is a group of optimal solutions that we have to study together in every situation. And the gas turbines are definitely one of those that may have a new future and a new application in the power generation grid, and in the future also of other fuels like hydrogen and so on. So we will have with this seminar the possibility to listen to some of these advancements and these new ideas. And that is the most important thing for the students to know and to learn about new ideas, new concepts, and having always the open mind to remind them when it would be necessary in the future. So I don't want to say much more than this. I would like just to thank again Dr. Rao. We will listen to him, and then I really hope that you will find the will and courage to speak up and ask questions, so that on anything he will say, and to have the most benefit of this from this seminar. So after this, I would like to leave the stage to Dr. Ashok Rao and listen to his talk.
Thank you, Professor Desideri. Thank you for the kind words, and I'm glad I'm able to participate in this important event. Let me bring up my slides, and I hope I don't have issues here. Do you all see my slides?
Yes, we do.
Okay, good. So the major focus of this seminar is innovations in gas turbine technology. And I'll be providing a very brief introduction on some of the approaches that have been considered or are being considered. These are listed here, starting with advanced firing temperature, all the way to something that's very much in getting a lot of attention, the pressure gain combustor. Now, in addition to this, I'm also going to touch upon, I just have one slide, on pre and post-combustion CO2 capture, which is a necessity if you're using fossil fuels for base load power generation. And then finally talk about what Professor Desideri mentioned about my lessons learned in the patenting power cycles. Now, what are the primary drivers for innovation? Of course, the first thing comes to mind is high efficiency. And of course, without compromising economics, as engineers, we want to have processes that are economically viable. Now, the US Department of Energy's stated goal is to take the current state-of-the-art combined cycle efficiency from 64%, this is on natural gas LHV basis, to as high as 70%. Now that's a real challenge, especially as we are getting closer and closer to the Carnot cycle efficiency. 6 points of increase from 64 to 70 is a lot more challenging, say from 44 to 50%. Now, in addition to reducing operating costs by having higher efficiency, this is due to a reduction in fuel costs. The side benefit is reduction in CO2 emissions on a per kilowatt basis. It's inversely proportional to efficiency, the emissions. Now, another major emphasis
sorry, Ashok. I think it's stuck on the second slide. I guess you have been talking about the third one. I don't know, it didn't change. Didn't switch to the third slide.
Okay. Is it the third now or still second?
Still second.
Oh my God.
I don't know if you would like me to try to show it. But
okay, yeah, that might be better.
Okay, let me see. I can try to act switching from. I can try to share my screen, and let's see if I can. Just one moment. You didn't find a way to. Okay, something happened. I don't.
Okay. Let me see if it works this way.
Yeah. Try again.
Okay. Do you see my third slide now?
Yeah. This is number.
Okay. So. Okay. Because I won't be in the presentation mode then. I'll just show this way.
Yeah. Okay. No problem.
Okay. So I talked about the DOE goals for high efficiency, which is taking efficiency from 64% to 70%. And a side benefit, of course, is the reduction in CO2 emissions on a per kilowatt basis. And the other importance being given is to have reduced environmental impact. And further reductions in CO2 emissions are possible by actually capturing the carbon and sequestering it in the form of CO2. Mm. Now, in addition to CO2, the NOx emissions are another important environmental concern. And the goal here for the DOE, the US Department of Energy, is to reduce the emissions down to 2 parts per million on a volume basis. This is without the use of selective catalytic reduction. I don't know if you're familiar with SCR, but it's where ammonia is injected into the flue gas of the gas turbine, the exhaust, where it reacts with the NO formed in a combustor to form elemental nitrogen. Let me just go back to the previous slide. Again, the diagram that
Sorry, we're still seeing the number 2. I don't know why. On the screen, we don't see your screen, or at least if you're moving, we're still on the lecture outline. But not, we see your PowerPoint, but not. It's not changing the image. It's stuck.
Okay. Oh my God. Let's see. Stop sharing. You're presenting to everyone. Okay.
Now we see.
So still you're on.
No, we see slide number 2, but if you try to switch. Oh, okay. Now we see it. Now it's 3.
Okay. Okay. How about now? Do you see 3?
Yeah. Now it's 3.
Okay. Let me just test number 4. Do you see 4 now? I'm in the next slide.
Not yet, but.
Are you still on 3?
Okay.
Or?
Now it's okay. Now it's number 4.
Okay. So let me go back to 3. The picture that I've shown here is a very simplified version of a combined cycle. A combined cycle is, of course, where you have a gas turbine as a topping cycle, and the Brayton cycle, and the Rankine steam cycle as the bottoming cycle. The diagram shown here is a very simple diagram, as I mentioned, for a single pressure steam cycle. Okay, so now we are back on 4, right?
Yeah.
Slide 4. Okay, good. Now this shows a full-blown modern combined cycle, a large-scale combined cycle, and this has 3 levels of pressure, steam pressure, and you have multiple pressures because what you want to do is minimize the irreversibility in the heat exchange in the gas turbine exhaust, and maximize the amount of heat recovery from the gas turbine exhaust. I won't go through the details of this diagram. A copy of this presentation will be posted, I understand, and you can look at it in more detail at your leisure. So let me move on to the topics, the various approaches, and I hope you see slide 5 now. Do you see 5?
No.
No.
It's so strange because normally the screen is.
So again, you don't see 5, I suppose.
Not yet. No. Now it's gone away.
You don't see. Okay. So, God. So I don't know what's going on here with. You are presenting.
Right. Now we see it. 5.
Okay. I'll just stay in this mode.
Yeah, I think it's better.
Okay. So next, I'll move on to this topic of advanced firing temperatures. And so, do you see 6 now?
Yeah.
Okay. So this is an interesting plot that was actually put together by the US Department of Energy. And it shows the evolution of firing temperature. What I mean by firing temperature is the first rotor inlet temperature of the gas turbine. Evolution of this temperature over a period of time. And as you can see, it's been steadily increasing. And also shown on this diagram are the combined cycle efficiencies, the overall efficiency. And this tremendous increase in rotor inlet temperature, the firing temperature, has been brought about by two things. One is advances in materials technology, both due to the coatings that are put on the blades of the turbine, as well as the base material, the metal temperature, the metal itself. And the other is the cooling technology, the advancement in cooling technology. Each blade in the high temperature section of the expansion is cooled from within. And film cooling is one technology that is not only cools from within, but also forms a layer on the outside of the blade to protect it from those high temperature gases. Now, as you increase the firing temperature, you also need to increase the pressure ratio. Okay, I hope we are all on 7 now. Slide 7.
No, still on 6.
Oh, God.
Okay, now it's 7. Now it's 7.
Oh,
Okay.
okay. Okay. There's a little time there. Okay.
Yeah.
Yeah. So the pressure ratio also has to be increased as we increase the firing temperature. And this is for two reasons. One is, for each firing temperature, there is a certain optimum pressure ratio, which tends to be higher as you go with higher firing temperature. Both have to increase. And the other is in order to limit the exhaust temperature of the turbine. The last stage blades tend to be very large because now you have the expansion gases near atmospheric pressure and high temperature. And to avoid cooling those blades, it's better to increase the pressure ratio and limit the exhaust temperature. Now, a consequence of this is that the compressor discharge temperature, which is the combustion air temperature, is higher. And this could lead to higher NOx emissions. And also with the premixed burners, this is where you're mixing, say, natural gas with air, the primary air, to reduce the flame temperature. There is the potential for pre-ignition. So that's something that needs to be traded off against. But there is one approach. Now, I hope we are on 8. Maybe
yes,
it makes a...
Yes, 8.
Okay. So one approach to handling this very high pressure ratios when we have a very high firing temperatures, especially in the future, is to have intercooling. This shows a 2-shaft machine with a low pressure compressor, high pressure compressor, with intercooling between the two. Having an intercooler can reduce the temperature of the high pressure compressor discharge to more than 100 degrees Celsius. And in addition to reducing the NOx, it also has a benefit of savings in materials of construction. Now, intercooling also increases the specific power output of the engine. On a simple cycle gas turbine, that is without the intercooler, about half the power produced by the expansion step is used in the compression step, with only the remainder half being available for net power. So if you have intercooling, say if you reduce the compression power by, say, 10%, then you'll have 10% more power available for export. Now, there are a couple of ways of intercooling. One is, of course, to have a shell and tube heat exchanger, but the big challenge with that is you need a huge amount of space for it. And shell and tube heat exchangers with, when you don't have very good heat transfer coefficients, can be very large and expensive. The other method is to simply spray water. Of course, it has to be high quality water into the airstream, leaving the low pressure compressor. This method of direct cooling has a couple of advantages. One is it reduces the size of the intercooler. The other is that you increase the amount of motive fluid, working fluid, for expansion. Of course, you have to compress the water vapor that you have formed this way by introducing spraying liquid water into it. The water evaporates. You have to compress it in the HP compressor, but also then you have more power in the expander because of the added fluid. Now, also, the NOx emissions can be reduced. You might end up typically introducing as much as 5% by volume moisture by spray intercooling. And water vapor, being a triatomic gas, has a much higher specific heat than, say, nitrogen or oxygen, and has a good beneficial effect on reducing NOx. Of course, the challenge associated with this type of system is more complex turbo machinery. Do you see slide 9 now?
Yeah, yes.
Okay, so we are in business now, I think. So next I'll talk about reheat and partial oxidation gas turbine. I emphasized the firing temperature so far to get high efficiency, but there is another approach to increasing efficiency without having ultra high firing temperatures. And this is with the reheat cycle. What we are talking about here is having a high pressure combustor. The compressor discharge goes into the high pressure combustor. Here you have partial expansion. Do you see my cursor if I move it?
No. Oh, yes. Yes,
Oh.
we see it. Yes.
Okay. So you have the high pressure expander, and which does partial expansion. And then the exhaust from here goes to the reheat combustor, where you burn additional fuel and then complete the expansion cycle. And this shows the temperature entropy or the enthalpy entropy diagrams for the conventional combustion, that is single combustor, simple cycle gas turbine on the left. And then on the right is that for the reheat cycle. You have compression, heat addition by combustion, expansion, partial expansion, again heat addition, and completing the expansion cycle. And the same amount of work can be produced, the same amount of specific power can be produced by not going to such high firing temperatures as you would require with the conventional combustion. In fact, I want to show some numbers here on the next slide, which shows a comparison between the GE 7FA, General Electric 7FA gas turbine performance compared to what used to be Alstom GT24, which is a reheat machine. This is, of course, now owned by also GE. It shows the firing temperature and the efficiency. The efficiency, in fact, very similar for the two engines here. But as you can see, the firing temperature is much lower for the reheat machine. So this is one approach to getting high efficiency without having ultra high firing temperatures. Of course, higher firing temperatures also helps the reheat cycle. A challenge, of course, with the reheat cycle is to take full advantage is to have much higher pressure ratios. So a combination of intercooling and reheat might be an interesting cycle to look at. Now, in addition, with an additional advantage of reheat cycle is not only reducing the, or not having to have very high firing temperatures, is to have, or is destruction of NOx. this is actually measured with the GD24 that I showed the performance for previously. What they found is the NOx that forms in the HP combustor was actually being destroyed, a portion of it was being destroyed in the reheat combustor. So on a net basis, you get lower NOx emissions because of the reheat cycle. And as I mentioned, you need much higher pressure ratios, which also means much higher temperatures for both the reheat combustor as well as the LP combustor. You're talking about in excess of 650 degrees Celsius. And for the LP combustor, the reheat combustor, you're dealing with the oxidant that has a much lower oxygen content. It could be less than 15% instead of being 21% with air. Now, there's another approach to the reheat cycle that is also being looked at. Gas Research Institute in the US was heavily involved in this, and DOE, the US DOE, was supporting it. And here what we are doing is partially combusting the fuel in the first combustor, the high pressure combustor of the gas turbine. So what you get is the combustion products are not CO2, water vapor, but instead mostly CO and hydrogen. And then this is expanded again in a HP turbine, partial expansion, then going into the second combustor, the reheat combustor or the oxidizing combustor, where the combustion is completed. And then you go to the LP turbine. Now, there are quite a few challenges associated with this. There's potential for increased efficiency again with reduced firing temperature, and the NOx emissions would be very low, especially in the HP combustor. You shouldn't have essentially no NOx formation unless you have not very good mixing, because the combustion is occurring at reducing conditions. And in the low pressure combustor, even though you have oxidizing conditions, you're dealing with a fuel now that has low calorific value. So in terms of NOx and efficiency, it's great. But then there are concerns due to metallurgy issues. When you have carbon monoxide at very high partial pressures, you can form carbides of the metal, and it can lead to what's called metal dusting. And you might have to add steam to avoid this, which ends up reducing your efficiency. The other thing is when you have hydrogen at high partial pressure, then it can lead to hydrogen embrittlement. That's something that again is a big concern. And so a lot of technology needs to be developed in terms of materials to handle such situations, such cycles. Next, I want to say a few words about what's called what I'm calling the preheat combustion air cycle. And here what we're doing is preheating the compressor discharge air before it goes to the combustor. Now, there are a couple of ways of preheating this air. This first option that's shown here is using solar thermal energy. And this has a big advantage of course, using solar energy. And at times when you don't have solar energy available, then what you can do is simply burn fuel downstream in the combustor. And this way you can maximize your capital, your investment throughout the year, throughout the night and day, And one of the disadvantages with the regular solar energy use is that it sits idle, in the nighttime. When on a cloudy day, the output is much lower. But here, you can vary the amount of fuel to adjust what you're getting from the sun. Now, to maximize solar thermal energy input to the system, you want to maximize, of course, the air temperature entering the combustor. And, I've been talking about some of the challenges associated with having hot air, very hot air, entering the combustor. There's potential for NOx formation. The cycles that have been evaluated involve preheating the air to as high as 800 degrees Celsius. And this not only would lead to high NOx formation in the combustor, but also the combustor itself will have some challenges. The combustor of a gas turbine has a liner where it's an annular space where the air first enters to cool the outside, the outer surface of the combustor, and that will become a bigger challenge when you have hotter air. This also means expensive or challenging materials for the heat exchanger, where the air is preheated against solar energy. But anyway, it's a very interesting cycle, and I hope the development of this continues. And now, a similar cycle has also been worked on. This is, instead of using solar energy for preheating the air going to the combustor, what we're doing here is using biomass combustor. So you have the compressor, and the compressor discharge is going into a heater, a furnace, where you're burning biomass and transferring the heat. And now the hot air is entering the combustor of the gas turbine and expanding it. And then, of course, you can have, a Rankine cycle, both in this case as well as the previous case. Again, here it's very similar. Biomass also has a certain seasonal characteristic to it. Certain times of the year, biomass may not be available. And again, here, what you can do here is increase the amount of natural gas or the fuel that you have available, the clean fuel that you have available to burn, to maximize, again, the overall capital utilization. Now, this cycle was, again, evaluated, this biomass-based system, project funded by the US Department of Energy. And what they found is that the overall cycle heat rate is the amount of fuel that you need to produce a unit of power. The heat rate was 10 to 20% lower than simply using a boiler to use the biomass. This is just a simple Rankine cycle. Of course, it depends on how much natural gas that you're burning in the system, along with the biomass. And the natural gas used was, in terms of energy input, less than 5%. Again, here, the challenge is the expensive metallurgy for the heat exchanger, because here they're looking at temperatures for the preheated air from 800 degrees to 1,000 degrees Celsius. And again, NOx formation. And if you have premix combustion, to reduce the NOx in the natural gas-fired combustor, then that's going to be a real challenge with this very high combustion air temperature. And the combustion liner temperature, challenges that I mentioned previously. Same things apply here also. Now, next, I'll talk about oxy-fuels. Now, this cycle has been developed with CO2 capture as the major emphasis. Instead of using air for the combustor in the gas turbine, what they use is oxygen. Oops. Oh. I hope we are all on slide 21.
Now we still see 20, but 20. Oh, now 21. Okay.
Oh, good. So this system was or is being developed by a company in Northern California. It's called Clean Energy Systems. And what they are doing is, in their cycle, they use oxygen, as I mentioned. And of course, oxygen will have to come from an air separation plant. If you have, say at the current time, you have cryogenic air separation, which unfortunately tends to be very expensive, both in terms of efficiency and cost. But assuming we can find cheaper ways of producing oxygen, you take oxygen and your fuel. If you have, say, biomass or coal instead of natural gas, then you'll have to, of course, convert that into a clean gas by gasification, where you have partial combustion of the fuel to make hydrogen and CO. Of course, that has to be cleaned up before you introduce into the combustor. So this section of the plant, the fuel processing plant, can be quite complex if you have dirty fuel. In any case, the cleaned up fuel or natural gas is combusted with oxygen. And in order to limit the temperature, the products of combustion, what you have is you introduce water into the combustor. And you have expansion. They are taking advantage of the reheat cycle that I described previously. So they have an high pressure expander followed by a reheat combustor where additional fuel is burnt, and then complete the expansion. And so the exhaust from this system is basically a mixture of CO2 and steam with some unused oxygen and any impurities that might be present, like nitrogen or argon. You take this stream, you cool it, and you condense out the water, and basically you're left with a very high purity or high quality CO2 stream that you can then sequester it. Various methods of sequestration are available that you can find in literature that are being investigated. Now, the combustor that they have for this application is from rocket technology. In fact, the inventor of this cycle was a rocket engineer. And the challenge, of course, here is that not only you're using oxygen, but also you're operating this unit, this combustor, at very high pressures. You're talking about in excess of 100 bar pressure. And they've looked at different ways of avoiding having excessive temperatures in the combustor, either inject water directly or inject water into the jacket of this combustor where it would form steam. And then the steam would then find its way into the combustion products. Very high efficiencies have been claimed in plants where CO2 capture is required by these inventors. Now, are we on 23 now?
Not yet. Try again. And 22, 22nd.
Okay. Oh boy. Did that make any difference? 20, is it still 22?
Still 22.
My God.
Try with the return button or the arrows. I don't know. So far, it's been going on quite well.
Just forward it and then.
No, it's broken.
Let's see if I can do this. So, oh my God. Let me try different things. Oh, shit.
Okay, now it's 23. That it was on 23.
Okay.
And then you switch back to 1.
Okay. Yeah, and then I'm back on 23. I think there's a huge amount of lag between.
Maybe. Let us wait a little bit. But,
yeah.
We still see number 1. I will tell you when we see number 23.
Okay.
Not yet. Okay. Now we see it.
Okay. Maybe the previous diagram took up a lot of time. Okay, so this just lists some of the challenges and the characteristics of this oxy-combustion cycle that I just described. One of the things that, as I mentioned earlier, was the production of oxygen is expensive, both in terms of efficiency as well as cost. It is using current state-of-the-art technology, which is cryogenic air separation. And so what you want to do is limit the amount of oxygen usage in the system, which means you want to operate the combustor near stoichiometric conditions. That is, have very little wastage of oxygen, because the oxygen is going to end up in your CO2 stream. And the other thing, of course, is that you cannot have too much oxygen in the CO2 stream itself. It's considered a contaminant from a sequestration standpoint, especially if you have to pipeline it and you have some moisture. You're going to have corrosion issues, and not only from the CO2, but now with the oxygen added to it. So, so that's operating that combustor under stoichiometric conditions is a challenge. You got to have good mixing to get complete combustion, and then you're dealing with very high pressure, partial pressure oxygen, and that itself makes certain metallurgical issues in the combustion process challenging. Okay, now I'm moved on to 24. Please let me know when you do see 24.
Not yet, but room 23.
Huh.
So strange that sometimes it works very quickly, and sometimes it blocks.
Yeah. I'm hearing that since because of COVID, there's a huge demand on the internet.
Yeah.
And
possibly we are quite from California to Italy. It's quite a long way.
Yeah. Okay, maybe I should try playing some games here.
Okay, now I see it.
Okay.
Now we see it.
Okay. So the oxy-combustion cycle that I described previously is the one that was or is being pursued by this company in Northern California, CES. But there's another approach to oxy-combustion that's being developed. This is called the Allam cycle, and that's the inventor of the process, Rodney Allam. And this is a cycle, as I mentioned, again, uses oxygen, but there are some variations to it. They don't have a reheat combustor as the previous case, but they have gone with the recuperated cycle. What that means is that in this particular case, they are preheating the oxidant in the exhaust of the combustor / turbine, the turbine exhaust, basically. Oxygen is being preheated and sent to the combustor for expansion. And then the recuperator provides the heat, and also the recuperator provides heat for some of the recycled stream that's used to limit the temperature of the gases within the combustor. Here, as you can see, the combustor and the turbine have been combined into a single icon. Again, here the challenges are similar. You're using oxygen, which is expensive, and the combustor has to be designed such that you minimize the use of oxygen, stoichiometric combustion. But one big challenge that I see is the preheating of this stream in the recuperator. This is the mixture of oxygen and some of the combustion products that are recycled. And you got to make sure that the oxygen content of this stream is not too high to make the metallurgy, you're able to build this recuperator with existing metallurgy. As you increase the partial pressure of oxygen, it becomes, it can even burn steel or iron. And so to me, in addition to all the previous challenges, what you have is this recuperator design. Now, a 25 megawatt pilot plant in Texas was being considered, and it was supposed to be scaled up to 300 megawatts by the year 2021. Not quite sure what the status is of this cycle now, but at this point in time, though, you need to have a home for the CO2 that you recover. You know, sequestration of the CO2, say geologically, is still under research and development. And I know there have been some successful test runs done in Canada and also in the North Sea, but still it's not commercially proven. So right now, a lot of the commercial viability of these processes depends on if you can sell the CO2 to the beverage industry or for enhanced oil recovery. Now, next, I'm going to talk about the HAT cycle, the humid air turbine cycle. This uses intercooling, kind of intercooling that I described previously, as well as recuperation, where the air is preheated in the gas turbine exhaust. Let me walk you through this cycle systematically. You have an LP compressor, an HP compressor with intercooling in between. And it's, again, a two-shaft machine, the HP expander driving the HP compressor, the LP expander driving the LP compressor, and the generator. You know, these two compressors have their own optimum speeds. Now, this intercooler is a shell and tube heat exchanger, not a direct contact cooler like the case that I showed previously. And the compressor discharge from the HP compressor discharge after cooling is directly contacted with hot water in a humidifier. And this way you're introducing a large amount of water vapor into the airstream, and this hot humid air is preheated in the gas turbine exhaust. This is the recuperator. And the hot humid air is then used for combusting your fuel, expansion. And then as far as the humidifier goes, for the evaporation of water, of course, you need heat. A part of the heat is supplied by the intercooler, the aftercooler, and the economizer that's in the very exhaust of the gas turbine. What you do is, in the humidifier, not all the water that's introduced gets evaporated, but only a portion, the remainder coming down, being pumped through all these various heat exchangers. Now, okay, I hope I can move on to the next one. Do you see slide 27?
Yes, yes.
Okay, good. Here, this cycle was being pursued heavily in the 90s. And United Technologies, a US company, they make aero engines. They got involved in it, and they did some experimental work on the combustor. The big advantage of this cycle is very low NOx emissions. And on a natural gas-fired HAT cycle, you typically have about 20% by weight water vapor introduced into the combustion airstream. And what they found is that the NOx emission was extremely low. They found less than 5 ppm/VD without use of an SCR. Now, another advantage with this cycle is that there's no steam bottoming cycle, the Rankine cycle. So that leads to a significant amount of capital reduction. And various studies have been done in this, comparing the efficiency of this HAT cycle to other gas turbine based cycles. And it's have found improvement in efficiency over the combined cycle. One big advantage is the essentially flat heat rate or the efficiency down to 60% load. Now, this could be a big advantage, especially these days with gas turbines used, as Professor Desideri mentioned, to complement renewables. You know, combined cycle, these gas turbine-based cycles will have to make up the difference when you have less renewable energy available. And this allows you to make up the difference without compromising efficiency. You can go up and down in power output all the way down to 60% without much of a degradation in efficiency. And the other advantage is that it's quite insensitive to ambient temperature. You know, even combined cycles suffer heat rate and output penalty as the ambient temperature changes, as it increases. Of course, this requires a more complex turbo machinery. And the combustor, you know, is you're dealing with air that's loaded with water vapor. NOx is low, but then typically whenever you reduce NOx, CO tends to go up. So what you need is a large residence time to minimize the CO formation. Currently, it's being pursued in China. The Chinese Academy of Sciences has built a pilot unit using an off-the-shelf gas turbine, and they are designing a gas turbine specifically for the hatch cycle, but at this point, without the intercooler. Now, finally, I want to talk about the pressure gain combustion. This is a very interesting cycle. You get a tremendous amount of efficiency gain. And the difference here is that instead of the conventional Brayton cycle that operates the combustor at nearly constant pressure, here we are operating the combustion process at constant volume. This is also known as the Humphrey cycle. And what we have found, again, the US Department of Energy was interested in UCI evaluating this cycle. We found the heat rate reduction could be as high as 7% by using this type of a cycle, keeping other variables same as a conventional Brayton cycle. This is on a combined cycle basis. You again can have a steam cycle as the bottoming cycle here. Now, most of the constant pressure combustors that I've seen operate in cyclic mode. I'll show you one example of it in the next slide. And the big challenge is really interfacing the cyclic combustion process with steady flow compressor and turbine. I hope you can see slide 31 now.
Yes, we do.
Oh, right. We're in business. This is one way of achieving constant volume combustion. Interesting paper was presented in Barcelona in 2006. But in this combustor, what the approach they have taken is to have channels in the periphery of a drum. Each of these channels functions as a combustion chamber, and it rotates between two stationary end plates. And these end plates have ports which are not shown. The end plates are not shown here. And each channel is periodically charged and discharged as the drum rotates. And premixed air fuel mixture and combustion products flow sequentially into and out of the rotating channels when they are properly aligned with the inlet and or the outlet ports. Now, the ignition occurs by hot gas recirculation from previously combusted channels through a feedback tube. Now, next, I hope you can see slide number 32 now.
Not yet, but
Okay.
let us see. Should come up. Still 31. Still 31. Okay, now 32.
Okay, great. Next, wanted to touch upon reducing carbon footprint. There are cycles, as I mentioned, that are specifically designed for reducing CO2 emissions. There was this oxy-combustion cycle that I described, which directly, or it's customized really for reducing this greenhouse gas emission. But on other cycles, what you can have is, depending on the kind of fuel, either post-combustion capture or pre-combustion capture. The diagram on the top right hand shows an example of post-combustion capture. You have your gas turbine followed by your steam cycle in a combined cycle mode. And here you have the CO2 that's present in the flue gases is treated in the CO2 capture process. And the captured CO2 is, of course, compressed to very high pressures before you can sequester it, before you can stick it into the pipeline and send it to geological sequestration. Now, this is so far, this kind of post-combustion capture was found to be more advantageous with fuels like clean fuels like natural gas. But if you have a dirty fuel, say dirty fuel from a gas turbine standpoint, especially a coal or biomass, then what makes sense is pre-combustion capture. This is removing the carbon from the fuel before the fuel is burnt in the gas turbine. So what you have then is a fuel that's mostly hydrogen that you're burning in the gas turbine. This shows an example, a front-end plant where coal or biomass is gasified, is converted or partially oxidized to produce a gas that's mostly hydrogen and CO with the help of oxygen obtained from an air separation plant. And this occurs at very high temperatures, so you need to cool it. This is 1,000 degrees Celsius plus. And you recover the heat and clean it up because you've got ash accompanying this gas. This gas is called synthesis gas. In the petrochemical industry, such gas was used for synthesizing chemicals, or syngas for short. And this gas, along with steam, is then reacted in a water gas shift reactor. Here, the reaction that occurs is CO reacting with steam to form CO2 and hydrogen. So now your carbon is mostly in the form of CO2. And then the CO2 can be removed downstream and sequestered away. And the remaining gas, which is mostly hydrogen, can then be burnt in the gas turbine. Then again, you have the bottoming steam cycle. Now, biomass is a renewable fuel, and one can argue, why do you need CO2 capture for biomass? But I see this as a good way of cleaning up the CO2 that's already existing in our atmosphere. I think this is a better way of going after it. Planting trees and harvesting them and gasifying it. So you have negative CO2 emissions. And it's better to do that, let the trees capture the CO2 rather than us building these humongous, very large scrubbers to scrub CO2 from ambient air, which is at very low partial pressure, the CO2. Now, there are various approaches to this CO2 capture process, shown here or here. Some involve solvent scrubbing. These solvent scrubbing processes are actually commercially available at current time, both for pre-combustion, or rather post-combustion and pre-combustion. And then also for sorbents are being developed. Again, they are very close to being commercialized. The challenge, of course, is that cost. The cost, there is, for example, with sorbents, there's a large amount of steam that's utilized for regeneration. Even with solvents, the large amount of steam that's required for regeneration of the CO2. And that causes a huge thermal penalty in the system. Now, membranes are also being evolved, and then a combination of sorbents and membranes. This is quite a exciting research area that's going on, CO2 capture from these power plants. Now, finally, I wanted to touch upon my experiences. Professor Desideri asked me to talk about this, as he mentioned, in fact, earlier. And wanted to talk about some of the challenges that one would face. First of all, what are patentable ideas? Yeah,
sorry,
because you're
still seeing number 32. I don't know why.
Okay.
But
Okay. Oh my God. Huh.
Now it's okay.
Okay.
33.
Okay. We've got 2 more slides, so then we'll be done. Okay, with the patenting challenges. What are patentable ideas? Let's talk about that a little bit. One way to patent an idea is to claim synergy. Synergy is where you combine, say, 2 or more existing ideas. These are, everybody knows about them separately, but you have come up with a unique way of combining these ideas. And then you end up with a result that's significantly better than, say, the combination or a simple arithmetic average of the 2 systems. And there are a lot of instances where synergy has been claimed. And in fact, to me, from a commercial standpoint, or from a evolving, getting the unit built, if you have a process that takes all existing pieces of technology and just combines them, puts it in a special way to get an unexpectedly high efficiency or advantage, it's really great. You don't have to invest too much money in evolving the technology. Now, the other patentable idea, of course, is having a totally brand new idea. You come up with, totally new idea, but it's kind of challenging, especially in power generation, which is a very mature field. Humans have been working on power generation for a long, long time. So coming up with a totally new idea is a bit challenging, and I would encourage people to think about the first option, synergistically combining known ideas. Now, one thing that's interesting that I found in my experience is that the patent examiner has a very different approach to looking at what's, if your idea is truly unique. We as engineers tend to deduce ideas. Just like we derive an equation, we derive an idea. We go through a logical sequence of thinking process and come up with an idea. In our field, the field of science, I think also, you don't have an idea just coming from nowhere. It's not like composing a new symphony or coming up with a new painting. But unfortunately, the patent examiner doesn't look at it that way. If we write our patent as if it was logically deduced, then the patent examiner, he or she, will think that this idea, well, if it's logically deduced, then it can be also logically deduced by anyone else, who's well versed in the field of the invention. And so that becomes a challenge. So the patent examiner will deem that idea as being obvious and will reject it. So I just want you to keep that in mind in the future when you come up with something that you consider patenting. And patent examiner considers it, or if it's a discovery, then it's considered it's favorable in his eyes or her eyes. If we can convince the examiner that it wasn't too obvious and it was a true discovery by accident, would be the best. Of course, as long as you're all not, how should I put it? Honesty, of course, is the bottom line, but when you write it, don't make it sound like it's too much of a deduction involved. Because, initially when I was writing patents, I took pride in the fact that an idea was derived by logic. And that doesn't quite go well with the patent examiner. So I'll leave it there, and I'll leave it to your imagination to figure out what I mean. Okay, and then the last slide, the last struggle of this seminar. Do you see my slide 34?
Not yet.
Okay.
Still 33.
Oh, okay.
Now.
Okay. Okay. And then next I wanted to spell out some of the steps that you would take for this patenting process. One thing very important to do is establish the conception date. You need to document it. And these days, with the electronic files, you do, as soon as you come up with an idea, you might want to draw it in Visio or whatever you have, or do a simulation. And that simulation file, even though it's not complete, you save it. And I think, I'm assuming that electronic files are acceptable. In the past, when I was a young man, used to maintain, calculation sheets by, we used to do a lot of work by hand, and we had to perfectly date it and, make a copy and send it internally in the department so that it's documented. And that's very important to do, because don't be surprised that if an exactly the same idea that you come up with is discovered by someone else on this planet. This it shouldn't surprise you, because human brains are quite similar and the laws of physics are same for all. And so, when you come up with an idea, or at least I did, when I come up with an idea, I think that it's like my thumbprint, it's very unique to my brain. But, I've found out the hard way that it's not quite true. Others can come up and about the same time as you come up with it. Because a lot of people around the world are working in a certain field, which is important at that point in time. So by documenting the date of first conception, it's important. It becomes very important when when another patent is cited about the same time. Then the first conception date takes the precedence. At least that's the law in the US. Now, next to what you want to do is do a thorough patent search, literature search, but especially patent search, to make sure what the prior art is, how your idea is different from it. Because one day you'll be facing this patent examiner or through the attorney. There'll be questions raised. Why is your idea different from theirs? And once you have established the conception date, performed literature, then you got to make a patent, what's called a patent disclosure. This is before applying for a patent. And here you describe your invention and prior art, and also, of course, mention your conception date, what documentations you have, and all the prior art. That's the literature search that you have done. And another important thing that you need to include in this patent disclosure is the usefulness of this patent and what the advantages are over the prior art. If you're working for a corporation or even for a university, someone has to shell out or spend the money to apply for a patent. This is the attorney fee and the filing fee. And then once you get the patent, an annual maintenance fee has to be paid, which is significant. And for someone to invest that money, they need to be convinced that there is financial justification for it. So the usefulness and advantage of this patent needs to be thoroughly documented. And what I mean by usefulness and advantage is what the market might be and how much, the bottom line is typically dollars or money, and how much money will a user save by using your invention. So with that, it completes the seminar. And if you have any questions, I'll be happy to answer.
Okay, thank you very much, very much. I think you offered a very wide view over gas turbine cycles, especially new concepts also. I invite the students to ask questions or make comments. Okay, let's see in the chat. Which is the technology that allows the solar preheating of the air in the hybrid cycle?
Yeah. I hope. Okay, this is one of the cycles. Do you see that slide 17?
Yes.
Okay. So, did someone have a question regarding this?
Yes, regarding how do you heat the air after the compressor with solar energy? Because actually, it's quite. You have to have quite a wide or big solar field, probably concentrated with liquids, with hot liquids, or I don't know how exactly conceptually how you transfer the solar heat to the air. If I have understood the question.
Yeah, there are different ways that people are looking at, and there's one company in California that was developing this system for preheating air, and what they were doing was preheating the air directly with the air. And as I recall, they had parabolic concentrators with the tube carrying this air, because you're heating it up to 800 degrees Celsius. And so they were doing it directly with the solar energy. And yes, that's the major challenge here, the preheater. Mm-hmm. And then of course the combustor, where you have this such huge, very high temperature air going into the combustor.
Okay. Well, if I can imagine, do you preheat directly the air exiting the compressor and then getting into the combustor by parabolic trough or something like that? But in that case, you add a huge volume after the compressor. So you can. Is it not dangerous to change so much the volume after the compressor for problems of surge?
Yeah, especially if the gas turbine trips, then you have this huge amount of air capacitance sitting there, and you'll have to quickly vent it before it starts. Otherwise it'll keep spinning the turbine.
Yeah,
you're right, and you have to have very high, very fast-acting valves to dump this hot air to the atmosphere.
Okay. There is another question I see from Eleonora Bertolucci. A lot of water is used in the hot cycle. What kind of water recovery systems are installed? This is the first question.
Okay,
the second question is, you answered the first one. Can you recover water from the hot cycle?
Yes. Okay, I'll go to the second question first. The exhaust can be cooled. A couple of ways of doing it. One is to use a heat exchanger, or to use a direct contact cooler. But the key is if you're using, if you want to recover the water, in order to save the water usage, then you've got to make sure that the heat is ultimately rejected to the atmosphere through air-cooled exchangers. You cannot use wet cooling towers, because then the wet cooling tower is going to, evaporate the same amount of water that you've introduced. In fact, more. And so the net usage of water will be actually higher. So what you need is a very large air-cooled heat exchanger in the exhaust, or direct contact cooler, but then the cooling water leaving the direct contact cooler will have to reject its heat through a heat exchanger. That's one thing. And University of Trondheim in Sweden or Norway, they did a lot of work in recovering water from the exhaust of the HAT cycle by using heat exchanger, not direct contact cooler. Mm-hmm. So it can be done, but it depends on the economics. first of all, the water usage of the hatch cycle, what we found is less than a combined cycle, which uses wet cooling towers. In the wet cooling towers is where you're using water, and the evaporation rate there is actually higher than the amount of water that you would lose in the exhaust of the hatch cycle. Now, the quality of water has to be very high for the hatch cycle, because you don't want any, in the humidifier, if you can see this diagram, 26, the water is being evaporated, no doubt, but there will be some mist carry over, some droplets carry over, even if you have a very good mist eliminator. And this droplets will carry with it any salts that might be present in the water, any dissolved material. And so that's why this water has to be demineralized. And but again, in our evaluation, what we found is that the raw makeup water that you use upstream of the demineralizer is less than the amount of water that you use in a combined cycle as makeup to the cooling tower. I hope that answers both the questions.
I think so. The second question is, nowadays we try to find alternative and more green fuels. Is it possible to use hydrogen and methane mixtures as a fuel in existing turbines? Would the performance remain good?
Yeah, in fact, yes. California especially is very much interested in ultimately going to carbon-free fuel, and there is a significant amount of renewable energy available here. And what they are looking at is slowly introducing hydrogen into existing natural gas pipelines and keep increasing it over a period of time with the ultimate goal of 100% hydrogen. But I'm not an expert in combustion, but some of my colleagues at UCI are doing work in this area. And as I recall, what they found is that I think you can go up to about 5% hydrogen in natural gas without any significant impact on the existing combustor of the gas turbine. Now, it will require, of course, some changes. You got a larger volume of gas coming to the combustor, and so if you are within the WABI index, then you're okay. But beyond that, you'll have to, the valve, the inlet piping to deliver the fuel may have to be modified, and then the exhaust temperature might be from the gas turbine might be higher because of the hydrogen introduced. And in fact, the working fluid temperature might increase. And one will have to look at the expander, the temperature profile through the expander, and might require some reduction in the firing temperature so that you don't go beyond the design temperature of the turbine.
Okay, thank you very much. There is another question about the recuperator in the Allam cycle. There is someone who would like to understand better how the recuperator works in the Allam cycle. Actually, we haven't talked in our courses about that cycle, so it could be useful if you can say some more words about it.
Okay. What they're doing here, of course, is you have the gas turbine exhaust, and
we still see number 26. Sorry.
Okay. Okay, I'm hoping it's going to come to 24. Okay, hopefully it'll show up. But yeah, a challenge here is, of course, to preheat the oxygen going back to the combustor. They are doing it by premixing some of the recycled gas to limit the oxygen partial pressure. And that's important from a metallurgy standpoint in the recuperator. As I mentioned, I think if you at high partial pressure of oxygen, it becomes the steel can catch fire. But but as far as they do show two streams being preheated against the exhaust. I haven't seen the details on the recuperator design, but in a combined cycle, you can stagger these. For example, the reheat and the superheat coils. You can have a portion of the reheat coils followed by a portion of the superheat coils. Again, repeat the sequence. And I would think you could do something similar to that over here. So, and the recycle streams are at high pressure, and you could have these going through the tube side, say just like a reheated steam in a combined cycle, and stream the gas turbine exhaust, which is at lower pressure. It depends on what the pressure ratio is.
Okay, now we see it. Listen, which is the limit for oxygen in the pressure to avoid problems with metals, with metallurgy?
Yeah, it depends. I mean, most of the work that we have done with using oxygen as a fuel, in oxy-combustion, is where we have limited the oxygen, as I recall. This is with preheated oxygen. I'll have to look up what the temperature was that we used for oxy-combustion. This was not in gas turbine cycles, but in a boiler plant. But we went as high as 60% oxygen, with the rest being mostly CO2. But the temperatures, there's a corresponding temperature to each oxygen, partial pressure. And the I don't recall the temperature offhand right now. But here, let's see what they have done. Now, stream number 9, they show 717 degrees Celsius. That's pretty high, and 312. So they must have a huge amount of recycled stream going back to limit the oxygen partial pressure. Okay.
There is another question. Thank you very much for the answer. And there is another question about the combustor developed from rockets design. The question is, oxygen and fuel are liquid when injected or are gases?
Okay. Oxygen in this case has been it's a gaseous oxygen. In the air separation plant, what they do is to minimize the power consumption in the air separation plant, the oxygen is vaporized. It's pumped first because of safety concerns these days. They're pumping it first as a liquid and then vaporizing it within what's called the cold box to recover the cold. Actually, so from an air separation plant standpoint, it's advantageous to provide gaseous oxygen rather than liquid oxygen. So the the work that we did for CES, the oxygen that was used was in the form of a vapor.
Mm-hmm. Okay, but could this, in this special case, could the cryogenic cooling from the oxygen also used for condensing the water for the CO2 recovery, or is it not possible, or wouldn't it not improve the performance?
Yeah, that's something interesting. That's a good thought. Typically, the oxygen, the air separation unit is so tightly designed in terms of heat exchange.
Yeah.
Very low delta T's, and the oxygen that typically comes out of the air separation plant in the form of vapor is, it's close to ambient but lower than ambient temperatures. Mm-hmm. But yes, you could use some of that. Use that air, oxygen rather. Yes, to condense if temperatures allow it. And this way, you could also, what you're doing is preheating the oxygen.
Yeah.
So good. Yeah, that's something that might be worth looking at.
Okay. Other questions from the audience? What about aircraft engines? Do you think there will be big changes in gas turbines for aviation industry? And do you believe Airbus saying it will market hydrogen aircraft by 2035?
Yeah, there is a lot of talk, and but I don't know how much of that is actually being given a real serious how much serious money is being invested in that area. But yes, hydrogen is getting a lot of interest for sure. At least in terms of what they say they might do in the future.
You don't believe so much?
I don't know. It's the specific hydrogen is a very low specific energy content, and I like to see it happen, but I don't know if it's going to happen. Probably not in my lifetime.
Well, I think maybe we will see some liquid fuels obtained by hydrogen, yes. Or yes. Even CO2 and hydrogen combinations in power to fuel technologies. That could be, but I still don't understand why we should load the aircraft with very heavy or liquefied hydrogen, which is also quite critical to keep. Instead of using, if we want to use a cleaner fuel, we have obviously the chance to do it by combining recovered CO2 and hydrogen from renewable energy. So it's clean anyway, even if it's not CO2 free in the emissions. But anyway, that's my idea.
Yeah, excellent idea. In fact, the Fischer-Tropsch process that's been commercialized during the Second World War.
Yeah.
It can be used. Yes, you're right. We can get the hydrogen from same old sources, and then yes, combine it with the CO2. Yes, or if you have even a biomass gasification.
Yes, of course.
Which are carbon rich, you can supplement the hydrogen to make Fischer-Tropsch liquids.
Yeah. Okay, I see Amir on the screen. Maybe he wants to say something, or other questions from the audience. Otherwise, we are almost approaching 7 here, and it's been quite a long seminar.
If there aren't any other questions, I'll do my final greetings. So, good evening to everybody. This seminar is coming to an end. And first of all, I would like to say thank to Dr. Rao for sharing your knowledge with us. And thank you for creating this opportunity. I also would like to apologize for the small technical issues. I hope that in the both meets that have been created, you have managed to follow the conference well. We're very happy to have had over 120 people attend this event. And we also like to thank Professor Desideri too. Without him, this event wouldn't have been possible. We hope that there will be further opportunities in the future to have other seminars, both with you and with the entire department DESTEC of University of Pisa. And last but not least, we'd like to thank all the participants,
Yes.
hoping that you have enjoyed the seminar. I'd like to invite you once again to follow us on our social media so that you can find out about the future seminars and initiatives. 2021 full of events is waiting for us. And we also invite you to participate to the conference organized for tomorrow by PIAnergy, another association part of our network. It's going to be about wave energy. So best wishes and have a nice rest of your day. Thank you. Goodbye.
Thank you very much. Thank you for your words, and thank you, Ashok. I hope to meet you again in Italy if you happen to come sometime in the future. You're always invited to visit us.
Oh, thank you, Professor Umberto and Professor Desideri. Sorry. And yes, I enjoyed the seminar and hope you've learned something here. So you all take care and stay safe.
Okay, thank you very much.
Bye-bye.
Bye-bye.
Thank you. Bye.
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 Thank you. Bye.